See lexical analyzer second part. Actually, in the last class, we have discussed about what is the role of lexical analyzer, how it is working in this compiler. Okay, it's always integrated with parser. Even though it is integrated with parser, we are having it as a separate unit. Why? Because we can do the job of scanning and tokenization in a separate phase, and then you can give the input to the parser whenever you need. Right? So it will help to simplify the design of compiler, and also it will help you to increase the efficiency of compiler. Okay, and it is not necessary to implement all the lexical analyzer program in a C or C++ program. You can do that in using some other tools, and you can integrate with it, right? So the portability is also enhanced in this case. So that's why we are going to have a separate lexical analyzer phase. So in this lexical analyzer phase, already we have discussed there are two parts. One is in that itself we are having, first you have to scan it, and then you have to produce the sequence of tokens. Okay. So let me once again summarize what are the things we have discussed in the last two classes. Token, it's token is having a pair. One is the token name, and the second one is optional attribute value. Okay. Pattern tells you the description of form of the lexemes of the token. Okay, how to create lexeme for the particular token. Okay, that description is given in pattern, and lexeme is the actual word which is present in your program. Okay, so if you are using a variable, that variable is in your program is a lexeme, and we have to check it out which token it belongs to. 5 types of token we have discussed. Can anyone tell what are the 5 types of token? Can anyone unmute and tell what are the 5 types of token we have discussed? Are you there, guys? Students, can you hear me?
Yes.
Yeah. What are the 5 types of tokens, ma? What are the 5 types of tokens? Are you listening? Those who have attended yesterday's last class, you might have answered what are the 5 types of tokens. Any one token type?
Ma'am, keywords, identifiers,
Yes.
constants,
Ah,
and then if and else.
okay, good. Keywords, constants, identifiers, punctuation symbols. One more thing, operators. Okay, these are all the five tokens. Very good. And when you are taking this tokens, when you are giving this expression like this, E equal to m into c to the power 2, right? So if it's given like this, the first one is consider as an ID, identifier token, and it will have a pointer to the symbol table entry in the attribute part. Okay, and second one is assignment operator. Third one is again an identifier. It will have a pointer to symbol entry, right? Symbol table entry, and multiple operator. Again, C is an ID identifier token, and exponentiation operator. And the last one is again a number, that is a constant. That value will be given in the second parameter. Okay, so these are all the things it will produce as an output of lexical analyzer. Okay, so when you read the content from the keyboard, or when your program is given as input to the compiler, first of all it will read the content, and for that we need a buffer. Okay, so the buffer will be looking like this, and we are having this end of file for each of the buffers, and that tells you that you have reached the end of that particular buffer. Once if you are there is a 2 pointer you have used. One is telling you lexeme begin. Okay, actually when you don't have any white spaces in between, so how will you differentiate one lexeme with other lexeme? Can anyone tell how many lexemes you are having here? E is one lexeme, okay, which belongs to identifier. Equal to is a lexeme, which belongs to operator. So we don't have any white spaces in between that. Then how will you differentiate this is a different one and this is a different one? Okay, so for that we need to have one lexeme begin. Sometimes you may have a sequence of characters, sometimes you may have a single character or alphabets or operators, whatever it is. So we need to have two pointers. One is lexeme begin and another one is lexeme forward. The lexeme begin will have the pointer, it will point to the starting character of a particular lexeme which is currently processing, and this one will go move on. This forward will move on reading characters until it reads a complete lexeme. Okay, so but by the time first time it's reading pointing this one and again it's pointing this, so double star is there, so it is not necessary to characterize this lexeme as a multiplication operator. You have to take it as an exponentiation operator. But when it comes to 2, it will come to know this is a separate lexeme. So lexeme begin will move from this point to this position. Okay, so that tells this double star is one lexeme that's been processed and that's been categorized as my exponentiation operator. Okay, so now the lexeme begin will point to 2. Again, the forward pointer will move to the next one. So if there is no characters or no content present in this buffer, you can also include that end of file when you are reading the contents from the keyword. So when it reaches this end of file, it will stop processing or it will stop scanning this. Okay, so this is what we have studied in yesterday's class also. I'm just yeah, this one we have discussed. If forward is at the end of the first buffer, you have to reload the second buffer processing, and forward will start from the beginning of a second buffer. The forward pointer will point to the beginning of the second buffer. Okay. Similarly, when the second buffer is completed, we have to reload with the first buffer. Okay. So that process is given here, right? So you keep on processing your content present in a program, and you need not wait for loading the buffer. So that is avoided as we are having two buffers here. So these things we have discussed in yesterday's class. And the next one what we have started in yesterday's class is regular expressions. So before going to start regular expressions, you know what is alphabet, what is a string. It's a finite sequence of symbols. And you might have studied what is language. It's a countable set of strings over some fixed alphabets. You will be having some alphabets, and that is used to create a set of strings, right? So that is commonly known as alphabets, and it is given by sigma. And in each language, there will be an empty string that is represented by epsilon. Okay. So what are the operations we can do in string operations? Concatenation. Concatenation is just to combine two alphabets, right? And identity, that means if you are multiplying that, or if you are combining an empty string with a string, it is equivalent to combining a string with empty string. Both are representing the same answer, right? And similarly, when you are coming to this exponentiation, we don't have exponentiation normally in our alphabets, in your regular expressions. So, but anyway, for a string, it is like s square, s cube, like that. It represents multiple occurrence of that based on the number of number present in this exponentiation. That number of occurrence of the particular string will be coming here. Okay, and the language operations are represented by these operators. First one is union, and what is the meaning of union, ma? See, I thought you people have already studied regular expression, so I can skip those parts. What is the use of this L union M? Yes, ma. What is the other operator to represent this L union M? What does it mean? It is taking alphabets from language L, or it is taking alphabets from M. Okay. So in both way you can represent, either you can use union or you can use R operator, right? Concatenation means you have to take the characters or alphabets from L, the language L, as well as from the language M. The content what you are getting from the language M is Y. So it is represented as the combination or concatenation of the alphabets from language L followed by the language M. Okay. And L power 0 represent epsilon. That means zero occurrence, that is empty string. And for any occurrence, L square is equivalent to L to the power 1 into L. Similarly, L cube is equal to L square into L. Like that, you can split it. So that's why in general, it's been given as L power I is equal to L power I minus 1 into L. Okay. So clean closure L star. Okay. 0 or more occurrence. And positive closure is 1 or more occurrence. Okay. So now here we are going to represent, or we are going to tell how to specify all tokens. Okay. So totally we are having 5 tokens, right? So that 5 tokens should be represented here. And when you are representing the tokens, you have to tell how should be, what are the rules to frame an identifier. That is given by this regular expressions, right? Here we are specifying what is the sample set of strings to be used for identifiers, and what is the sample set of strings to be, our simple set of strings to be used for operators. Like that, you have to tell what are the possible alphabets or operators you have to use it. That will be given by the set. And also you have to tell the rules how to frame that identifiers or how to frame the operators. That specification is given by this regular expression. Okay. And this regular set is nothing but the set of alphabets, whatever you have used in your regular expression is known as regular set. Okay. And here we are taking the representation, how to explain regular expression. Epsilon is a regular expression denoting language L, right? And for each and every alphabet belonging to the particular language, you can express it in the form of L of A, right? That is given by A itself, right? You can give it as A, right? For example, if I am having 3 like this, 0 and 1. So in my regular expression, I can use it as 0. That is, a language for 0 can be represented like this, or O like this, you can represent. Okay. And the operations, what you can do in regular expression is similar to the operations in strings, right? Strings or language. The first one is RRS, which is equivalent to the content from either the language R or from the language M. Second one is R into S. We have to take the language content from alphabets from language R as well as from M. And R star, 0 or more occurrence, R, that is a singular. Okay. And these are all about the operations in regular expressions. Okay. Now, whenever you are using operators, you have to tell the precedence, which has to be processed first, right? So clean closure will be the having the highest precedence, then concatenation, then the least one is your union operator or operator. Okay. And algebraic clause for regular expression. Can you write A or B is equal to B or A? Both are same. You are going to get the content from either the language R or from languages. So it is commutative. And when you are taking the second one, it is associative too, right? You can combine more or operations like this, and you can make it as an associative one. And when you are taking this concatenation, but concatenation is not commutative one. Okay. So if you are taking this R into S, this is not equivalent to S into R, because you are going to take the alphabets from the language R, then it should be followed by the language S. This will not be similar to the content from language S followed by language R. Okay. But it is distributive, so we can write like this: R into S, R into T. That is, we can combine this R operator as well as concatenation operator like this, right? And identity already discussed, and this is we can write R star as RR epsilon string, right? And idempotent. Okay. So the next one is regular definitions. So when you're having when you're having a regular definition, set of regular expressions, we can group that and you can make it as a regular set, right? So, for example, when you're having a digits, right? When you're representing a regular expressions for digits, we may have 0, 1, 2, 3, up to 9. Okay, so instead of telling that these are all the alphabets we are using, you can make it as a complete set and you can represent by a definition. So D1 represents all the alphabets present in the regular expression 1. Like that, you can create a regular definition. Okay, so let me show you one example. So this is the regular definition. See here, when you are using all alphabets, normally in your variable you are going to use all alphabets, right? 26 uppercase as well as 26 lowercase alphabets will be used there, and you can use underscore, right? But other than this underscore, we are not going any other operators in identifiers, so we can group all these together. These are all the possible alphabets, and you can give the definition as letter. And similarly, for the digits, you can give the definition as 0 to 9. Okay, so now we can frame what is the regular expression for identifier. So when I'm using a variable, it should be a letter followed by letter or digit star. Letter means it will take that value from either uppercase alphabets or lowercase alphabets or underscore, followed by 0 or more occurrence, right? So it may have a set of strings. This regular expression will accept set of strings like this, any alphabets, M. It may have a single character, right? So that time this second component is star, means 0 occurrence, right? In case if you are taking one occurrence from letter, then it can generate a string like this, MS. S is any one of the letters I'm randomly selecting, right? Or it may be M0 or it may be M2. Likewise, you can generate any set of strings which is following this particular specification, right? So this is what regular expression is, right? You can give that regular expression as a regular definitions by, instead of representing all these A to Z, wherever you are using it, you can represent by a common name. That common name is given as regular definition. Clear with this? Any doubt?
No, ma'am.
Okay. So now some of the definitions we can move on. We can represent definitions like this, 0 to 9, or capital A to Z, small a to Z, like this. Or you can give if, then, else. For operators, relational operators, we can give like this. For identifier. And in the case of numbers, it may have a single digits or multiple digits. So what you have to do is, the first one should be a digit plus. Okay. So the digit plus means at least one occurrence of the digit should be there, followed by digit plus one or more occurrence. If I'm giving question, means what does it mean? 0 or 1 occurrence only. Okay. And then followed by E. That means this one is given in the form of normalized form, right? You have to represent E plus that exponentiation part you have to give, right? So exponentiation followed by the sign for that number followed by the digits. Okay. And so these are all the lexemes which is used in your program. We are categorizing according to the token and what attribute value it belongs to. In case of, you can easily see that here, in the case of identifiers, we should represent the second attribute as a pointer to the table entry. In the case of numbers or constants, you have to tell what is the corresponding value present there. So that should also be saved in the symbol table. But normally, it will be used in a separate memory, and you can represent that. You can give the value of the memory address, right? And all these are relational operators. You can mention them. So far we have discussed how to specify a token, right? So for specification of tokens, we are using regular expressions. Okay. Now we are going to recognize that token, right? What is recognition of tokens? What is recognition of tokens? If you are giving a lexeme A3 based on the regular expressions rule, it has to recognize which token it belongs to. Okay, I am having the regular expressions which is telling the way to represent to identify token. Now using that as a reference, I have to categorize this lexeme as identifier. If I am giving this as input based on the regular expressions, it has to tell whether it belongs to operator like this. So to perform this job, for recognition of the tokens, which token it belongs to, which token this particular lexeme belongs to, we need one machine. That machine is finite automata. That finite automata is represented here in the form of a transition diagram. So it will be having a starting state, and for all these operators, you can represent like this: equal to operator, greater than, and all the other operators we can have states. Once if you reach the end state, you can give the result as this particular lexeme belongs to relational operators and it is lesser than or equal to. For example, if I am giving less than, okay. In case if I give greater than means, then if the input is greater than means, then it will go for the corresponding. So it will come here, right? Again, it will check it out. Either it is having only greater than or it is equivalent to greater than or equal to. If it is followed by equal to, then you have to categorize that operator as greater than or equal to. Okay. In case if greater than is followed by some other identifier, then you can categorize this particular lexeme as greater than symbol. Okay, that's what given here. The transition diagram is, if you are new to this finite automata, this is just like it will try to tell you how to categorize these lexemes, right? To the corresponding tokens. Okay. So, but you people have already studied all these finite automata. So just to map, just you have to map the concepts, whatever I am telling here with respect to the compiler, right? And start. This is for identifiers. Letter should be followed by letter or digit. So it is a self loop, and it should be followed by other, right? So get token, it is categorizing this token as identifier, and install ID will help you to save the content in symbol table. Okay. So similarly, whatever you have done in the transition diagram, the same can be represented as a form of a program, right? So this is the function for recognizing token, and this token is relational operator tokens. So you can write the code like this. While of 1, you have to repeat it. In the case of 0, get the first operator and check it out. What is the next character? If the first character what you have read is a greater lesser than symbol, then you have to move to state 1. Okay. So in the previous example, the transition diagram, what you have done is we are starting from 0, and then at the time when you are reading this lesser than symbol, it is moving to state 1, right? After reading that, if it is equal to means go to state 2. If it is greater than means this is not equal to, right? Go to state 3. And if it is having some other thing means, then you have to categorize that as lesser than symbol. Okay. So that the same thing, whatever you are doing in the transition diagram can be implemented like this, right? If the first character is lesser than or equal to, next you have to move to state equal to 1, and the next character is equal to means go to state 5, and if it is not equal to means go to state 6. Can you map these two relational this program with your transition diagram? Okay, because only if you map these, then only you can do you can write the programs in lab sessions, right? Similarly, for each tokens we have to categorize like this. I'm giving only an example for relational operators. Likewise, you have to do for identifiers.